Okay, so what is a chemical reaction? And the chemical equation shows you what happens when we start with some chemicals, and those chemicals have the potential to become more stable. And when that happens, you form products. So that's the driving force why anything happens. And we've talked about this numerous times throughout the semester, and it's a very solid concept. So things go from unstable to stable. So if you have some reactants, starting materials that have the potential to get more stable, that's the driving force. That'll happen. Now there's some barriers there that can slow that down, but basically we're looking at that's what you start with. Reactants. And that's simply things like in this room, we've got a bunch of gases. We have nitrogen gas, oxygen gas, carbon dioxide. Those are reactants. Now, the question is, will those reactants want to change and become more stable? So in the case of our atmosphere in here, the reactants are more stable than the products that they might produce. So that means nothing happens. If we take hydrogen gas and oxygen gas with a little bitty spark, we produce a huge explosion. It's called water. Water is very stable. Water is more stable than hydrogen gas, H2, and more stable than oxygen gas, O2. But it doesn't happen spontaneously. We need something called a spark. Okay, so what are reactants? Those are atoms or molecules. Products are atoms and molecules, but more stable. Now, for the reactants to become more stable, you have to break bonds. So when we started with the H2 and O2 for making water, the H2 bonds have to be broken and the O2 bonds have to be broken. That requires energy. That's known as a spark. Once we put that spark into that mix, then the bonds can be broken and rearranged to a more stable product, water. Now, that new product is much more stable than that which you started with. Okay. So if we look at something called potential energy, there's two kinds of energy in the macro world, potential energy and kinetic energy. The sum of those two is a total energy for that system. And those two are interchanged back and forth. One's converted to the other's converted back, etc. Okay. The potential energy is stored in the bonds. Okay, so if we start with the reactant side and we look at the potential energy over here, that's a certain value. It depends on what you're starting with. Now, if the product potential is more stable than the starting materials, the reactants, what's going to happen is we're going to convert that potential energy in the reactants to kinetic energy. Because notice down here, the products have less potential energy. So that difference between the product's potential energy and the reactant's potential energy is converted to kinetic energy. That's known as heat. So this energy given off is usually observed as heat. Now, heat is a measurement of kinetic energy or the movement of molecules or atoms. The metric we use to measure that is called temperature. So in other words, if reactants go to products that are more stable, heat is given off, temperature rises. So let's go back to making water. H2 gas, O2 gas. Give a little spark, it makes water. Now the difference is huge between potential and energy of the product and reactants. Huge. One example it's so huge that NASA uses it as a fuel for rockets. It's called liquid hydrogen, liquid hydrogen. They mix them together and kaboom, the rocket goes up. Lots and lots of energy. So this difference here is quite dramatic. Now, to get this to happen, it just doesn't happen spontaneously, unless you have something like trinitrotoluene, TNT. Then all you need to do on that is shake it a little bit and kaboom. Dr. Nobel invented dynamite. And what he did is he made TNT safer because he saw a lot of civil use for dynamite. Unfortunately, they also turned it into something called a bomb. But he received the Nobel Prize for that. And they named the Nobel Prize after him. Well, the first Nobel Prize was creating dynamite. And there's a lot more explosive stuff made since then. Explosives is a very interesting science. Okay, so bottom line here is we have to put energy into this thing somehow, whether it's shaking the TNT or a spark or something like that. Okay, so basically what we're doing there is we're increasing the potential energy of that system because we got to pull apart those bonds. It takes energy to pull apart those bonds. Okay, when that happens, we have a mix up here of atoms. And the fancy name for that mix is called activated complex. Now, once that happens, notice that energy is high, the potential energy. So those atoms want to become more stable. There's two places for them to go where they're more stable. On the left and the right. They go on the left, they recreate the reactants. They go on the right, they create the products. And there's a mix. There's a topic when you get into 1A and possibly 2A. I'm not sure how much it's covered. It's called equilibrium. And that ratio, once the reaction starts of products and reactants, there's a ratio, and that's called the equilibrium constant. So whole study. Okay, so what happens is if the products are more stable than the reactants, then more of the products are going to form than the reactants. So this is what the graph looks like. This difference here is how much energy is given off. Now, when you get into more chemistry, instead of potential energy, they talk about something called Gibbs free energy. Gibbs free energy is a mixture of potential energy plus randomness, entropy. Those together make up Gibbs free energy. And it's a more accurate way of determining what's happening with the reaction. Okay, two things happen. Conservation of mass. You start with 10 grams, you end up with 10 grams. If you end up with 9.9 grams instead of 10, it has to be accompanied by a huge explosion. It's called E is equal to MC squared. So energy and mass can be interconverted via that equation. At our level, 10 grams equals 10 grams. We're talking about at the nuclear level, that doesn't always happen. Okay, and also the number of atoms. If you start with 5 hydrogens, you got to end up with 5 hydrogens, unless you're talking about nuclear chemistry. But in non-nuclear chemistry, you start with 5, you end with 5. Start with 10, end with 10. And number 2 is a part involves balancing equations. It's a conservation of the number of atoms. So basically, if we look at a chemical reaction, let's okay, so let's look at this reaction here. We have methane. This is oxygen gas, carbon dioxide, and good old water. Okay, and this whole reaction is called combustion. So combustion requires a fuel. Fuel can be lots of different things. Requires something to oxidize the fuel. In this case, it's oxygen gas, but it can be other things as well. And what happens is if we oxidize the fuel with oxygen, we get carbon dioxide and water. Now, I have an activity for you to do at home tomorrow morning. We're going to use gasoline as a fuel and oxygen as it's called an oxidizer. Start up your car and run around to the tailpipe and see what's coming out of the tailpipe. You're going to notice that water is coming out of your tailpipe. Then the water disappears. Why does the water disappear? It's not disappearing. It's just you can't see it because it's gaseous water, also known as steam. Have you ever noticed in the sky I live in Natomas, which is near the airport. So there's lots of contrails. Who's heard of a contrail? Okay, what's a contrail? It's a white thing in the sky, right? Oh, chemtrails. Have you heard of Art Bell? Look up Art Bell online and chemtrails. This is out of the 60s. This is really old stuff. I used to drive a lot in the 60s. Sorry, this is an aside. I used to drive a lot in the middle of the night and I listened to AM radio. This is back when your car had AM radio and there were stations. And Art Bell was a radio announcer. He talked about all this stuff. One of the conspiracy theories that he used to promote was something called chemtrails. And what you saw, those white streaks in the sky, were chemicals that were raining down upon us, were bad chemicals, and they were polluting our system. Not exaggerating. And he had guests on that were observers of this. You know, they watched planes being loaded and all this stuff. Well, really, what a contrail is the water being produced from jet fuel. And because it's so high up, it turns to ice. That white stuff you see in back of planes are ice crystals floating because they're very, very small crystals. Now, of course, Art Bell would say, yes, it's ice, but it's also got chemicals in it, other things. He's always big on that. Anyway, look him up. You'll find very interesting. Okay. All right, so number 2 here is conservation number of atoms. So what we're doing is we're going to do an inventory of the atoms, and the inventory is going to be on the left side of the arrow and on the right side of the arrow. The left side of the arrow are reactants, the right side of the arrow are products. Now, what's on the left, number-wise, has to be equal to one on the right side. So what do we have on the left? Well, we have carbons, hydrogens, and oxygens. So the carbons on the left have to equal the carbons on the right. So the conservation of numbers is maintained. Hydrogens on the left, hydrogens on the right, oxygens on the left, oxygens on the right. Okay, so let's do an inventory. Let's start with the reactant side, the left side. Okay, we have, now notice there are no numbers in front here. There are two kinds of numbers in a chemical reaction. There are coefficients, which are the numbers out front, and we have subscripts, the numbers below. The numbers below cannot be changed. No exceptions. The coefficients is how you do the inventory. So coefficients change, yes. Subscripts, no. No exceptions. Okay, so if there's no number in the front, no number for the coefficient, it's the same as 1. So that's what we start with, 1, 1, 1, 1. Okay, so let's count carbons. How many carbons are on the left? 1. What about on the right? 1. We have 1 CH4, that means we have 1 carbon. How many hydrogens do we have on the left? 4, because 1 times 4 is 4. Okay, on the right, we have 2. So right away, we have a problem. Carbons are fine, not hydrogens. Oxygens, we have 2 on the left, 3 on the right. Again, we have problems. So what we're going to do now is change the coefficients so that our reactants equals the products in terms of atoms, not molecules, atoms only. So if we change the 1 over here to a 2, that's going to change the number of atoms on the right. So now hydrogens become 4 because 2 times 2. And that brings our oxygens up to 4. Because we have 2 over here, 2 over here. That's 4 total. All right. So carbons are good, hydrogens are good, oxygens are not good. So one way to kick up the hydrogens on the left is to put a 2 here. And then 2 times 2 is 4. Now, when we achieve this 1, 1, 4, 4, 4, 4, that's called the equation is balanced. So when you balance an equation, this is what you do. You fuss with the coefficients till the left is equal to the right. Now, what's the method? There are 2 methods to do this. One method is called guess and check. Guess is you change the coefficient and then you do an inventory. That's the check part. Guess and check. The other part is using a sophisticated matrices. Sounds like a movie. And we use a system of equations to figure it out. And that works really well, but it's a pain. And we're not going to do that because none of you had linear algebra. That's the class you take after differential equations. So guess and check is our only tool. All right, does that make sense? In its simplest form, we want the left to equal to the right. Now, when we do stoichiometry, step number one is there a chemical reaction going on? If the answer is yes, then you have to write out the equation or the reaction. Now, for this class, I'm going to give you the reaction. In your next class, depending on who teaches it, you may or may not be given the reaction. You may have to figure out the reaction. Okay, and then you have to balance it. So that's step number one. If there's a chemical reaction, balance it. The rest of the stoichiometry, 3 more steps, depends upon step number one. So if you can't balance the equation, you get the whole problem wrong. All right. Are there any questions about this particular balancing? Yeah. We have 2 waters. Okay. That means each water has 1 oxygen. That's 2 oxygens, right? And then the carbon dioxide each one has 2 oxygens. So 2 from the carbon dioxide and then 2 from the 2 waters gives us 4 total. That makes sense? So you want to look at the sum of all the atoms, not just one of the parts, the sum on each side. The sum on the left got to be equal to the sum on the right. That's why when we ended up with 4 oxygens, we needed to kick up the O2s to 2, so we get 4 oxygens there. Now, sometimes this can get quite complicated. Now, for your next test, I have an extra credit problem for you. And it's, let me just show you where to find that. So since you have a whole week off and you'd like to try this, I'm going to go to Canvas Files, like always. And by the way, I've got lots of worksheets for you on practicing balancing equations. That's the extra credit problem. So that's not balanced and it's hard. Otherwise it wouldn't be extra credit. So if you want to do that, bring that in with when we take test 3, just you'll end it at the same time. Okay, so let's practice some more of this. Okay, so let's do ethane. Instead of methane, let's do ethane. Ethane is a 2-carbon fuel. We burn it in oxygen as the oxidizer. That's going to give us carbon dioxide plus water. By the way, one of the take-home problems for test 4 is you're going to actually calculate how much ice is made when you fly from Seattle to Los Angeles. Yeah. Okay. All right. So first thing is do an inventory. Okay, we got C's, H's, and O's again. Okay, we got 2 carbons on the left. Remember now, coefficients are all 1 to start with, and 1 on the right. Immediately we got a problem. 6 oxygens on the left, hydrogens on the left, 2 on the right. 2 oxygens on the left, 3 on the right. Okay, so this thing's all messed up. all messed up. So what are we going to do to fix it? Well, one thing we can do to fix the carbons is to put a 2 here. That'll make our carbons 2. But our oxygens now are changed because of that. So we got 4 here and 1 there, so that's 5. Okay, hydrogens. 6 on the left, 2 on the right, so let's put a 3 there. That gives us 6 hydrogens. It changes the oxygens again. Okay, so we've got 4 oxygens plus 3 is 7 oxygens. 2 on the left. Okay, now this is the challenging part. How do we make O2 7? What's the coefficient? What do we multiply 2 by to get 7? 3.5. Okay. 3.5 or 7 over 2 times 2 is 7. So it's balanced. However, there's a problem, is you cannot have fractional coefficients. So the first step is to balance it. And sometimes you have to use fractions, sometimes you don't. Now, some teachers will tell you, oh, stop. You cannot have fractions. So then they go through all these other steps to fix that. The easiest way, in my opinion, is just to clear, after we balance it, we clear it of fractions. Do that in one step. To clear the fraction. So how can we make 7 over 2 not 7 over 2 fraction? We multiply it by what? 2. But what we do to that, we have to do to everything else. Remember, this is like an equation. So this is a 1, so that becomes a 2. This is 7 over 2 times 2 becomes 7. 2 times 2 is 4. 3 times 2 is 6. Okay, so let's do an inventory now to make sure we balance this equation. Okay, so in carbons, we have 4. 4. Hydrogens, we have 6 times 2 is 12. 6 times 2 is 12 over here. Oxygens, we have 7 times 2 is 14. We have 8 here, 6 there is 14. So now it's balanced without using fractions. So fractions are fine to do the initial balancing. Just don't leave it as a fraction. Now, the reason why we can't leave it as a fraction is because there are 3 things well, actually, let me back up. Under conservation of number of atoms, we can't have part of an atom or molecule. And a fraction is a part. So whenever we balance an equation, chemical reaction, what we're saying are 2 things. It's a mole relationship. And a molecular relationship. And this is via coefficients. So in other words, once we balance the equation, that means 2 moles of ethane, C2H6, plus 7 moles of O2 gives 4 moles carbon dioxide plus 6 moles water. Or 2 molecules of ethane plus 7 molecules of oxygen gives us 4 molecules of carbon dioxide and 6 molecules of water. So molecules and moles can interchange on the balanced equation. That's why the word mole came from molecule. They're very closely related. So a typical test question is, what information can you gain from the balanced equation? 2 things: the number of moles relationship and the number of molecules relationship. Put a little star by that. You will have that in your next test. Okay. All right. Now, this appears to be pretty straightforward. This can get quite challenging, though. Quite challenging. Using the guess and check method. By the way, the average time people spend on balancing the extra credit problem is 90 minutes. Just FYI. Using the second method, the matrices method, it takes 52 seconds. And that's how long it takes to set up the matrices in your calculator. Press a button and it's done. Yeah. Oh, sure. Sure. In fact, if you want, send me an email and I'll send you the, what kind of calculator you have? You remember is it a TI? You remember the number? Okay. Yeah, send me an email. And yes, you may use that all the time. Now, sometimes guess and check is quicker, but like the extra credit, I'm not exaggerating, 52 seconds. And it's amazing how much faster it is. But you got to set it up and you have to understand matrices. And what you do is you assign each atom a variable. So if you have 5 atoms, and you have 5 equations, and anyway. Okay. All right. Are there any questions about balancing? Okay, so I'm going to do another example here. And let's see. Okay, so we have iron nitrite plus sodium sulfate gives us sodium nitrite plus iron sulfate. So it's a chemical reaction. In fact, this is called a double displacement reaction, and we're going to study those as a separate lecture topic. But for right now, it's just a general chemical equation. Reactants and products. Okay, notice I had to use parentheses. That's because the common ion nitrate, NO3, is a group, and its charge is -1. Sulfate, SO4, it's also a group. Its charge is -2. So this is iron 2 nitrate, sodium sulfate, sodium nitrate, excuse me, and then iron 2 sulfate. Now, iron is in the middle. Those ones in the middle in the periodic table can take on multiple charges. That's why I have to say iron 2, iron whatever. The sodium is on the very left. It always is a positive 1. The nitrate is always a negative 1. Sulfate is always a negative 2. Okay, so first thing we're going to do is do our inventory. So we have iron, nitrogen, oxygen, sodium, sulfate. Now this ends up being complicated. One, because we've got lots of different atoms there. Okay, the other way to look at this problem is, notice we have a nitrate here and a nitrate there. If that's the case, it'll save you time. Also notice we have a SO4 and an SO4. More time savings. So if you find a common ion on both sides of the equation, we're going to treat this slightly different. So instead of separating the oxygens from the two ions, we're going to treat them as different oxygens. So the NO3 oxygen is different than the SO4 oxygen. So what we're going to do is we're going to say NO3 is like X. SO4 is like Y. So we are now going to redo the inventory. So instead of iron, we're going to have iron, and we're going to have sodium. But instead of NO3, we're going to have X. Instead of SO4, we're going to have Y. So how many irons do we have on the left? 1. How many irons on the right? 1. How many X's do we have on the left? 2. How many Y's do we have on the left? 1. X is on the right. And this is X. This is Y. 1. And how many Y's on either side is 1. Now, see how much simpler that is? Now, this only will work, and I want to emphasize this, only will work if you have ions that are the same on both sides. If they're not the same, you've got to do just the original approach, taking everything apart. Okay, so now let's balance this. Okay, the irons are fine. Oh, the sodium, do we have 2 here? 1 there. Okay, so where do you want to start? The irons are fine, so let's not mess with the irons. Want to go to sodiums? All right, let's do the sodiums. Okay, now the coefficient here, we're going to make 2. So that we end up with 2 sodiums and 2 X's. Okay, what about Y's? Well, we've got 1 Y and 1 Y. 1 iron, 1 iron. 2 sodiums, 2 sodiums, 2 X's, 2 X's. It's balanced. Now, see how much simpler that was by looking at groupings. Now, the groupings, again, I want to emphasize, will only work if they're the same on both sides. Now, your dry lab on equations is not the same as in your packet. I'm going to give you a slightly different version of that. In my version, you only practice balancing equations. The packet's got all these other flavors in it, and to me, it's confusing. It doesn't focus on balancing equations. So the dry lab equations I forgot whether that's the week you get back or the next week later. You're gonna be using a different set. It's gonna be, where is, I guess I need to put it in. Last semester did it. I don't understand why it's not here. Anyway, I'll alert you to that. So that's coming up. It's not soon. Okay. So are there any questions about balancing equations? This is just doing a bunch of them. And it's going to be an aha moment when it goes, oh, all I need to do is make sure the left and the right are the same. I mean, that's just netting it out. But the importance of it is extremely important because of stoichiometry reasons. It's the first step. Now, remember, if we go back to unit 1, I gave you 4 steps to solve all those problems. The first step was balance the equation, remember? And I said, we're not having a chemical reaction. So we skipped step number 1. What's given? What are we trying to calculate? And the setup. So now we're going to bring in step number 1, particularly in unit 4. Okay. That's what I wanted to cover today. Balancing equations. You need to practice this a lot. If you've never done this before, and I'm assuming the way I teach this class is I'm assuming no one's had this before. If you've had it before, that's fine. But if you've never seen this before, it's crucial that you do a bunch of problems. And if you go to Canvas files, here are all the worksheets on balancing equations. Lots of practice. Now look at problem number 9. That is a very hard problem if you don't group it. So we have NH4 on the left, NH4 on the right, NO3 on the left, NO3 on the right, PO4, PO4. So this is a pretty easy problem if you group it. And it's an awful problem if you don't group it. This is a pretty challenging problem, number 9. Yeah. Yeah, and only you wouldn't, when you're all done, you convert the X's and Y's back to the original. So with the coefficients, you have coefficients. Yeah, so this is going to be a 1. This is going to be a, this is a 1, 1, 2, 1. Yeah.
But this is how you complete it on problem.
And if I asked you, show me that this equation is balanced, this is what I want to do. These guys, because that shows that the left and right are equal. This concept makes sense. The concept is straightforward. It's just doing it is requires practice.
Iron. It is. Is it? Metal? Yes. Is it really? Yes. Yes. Is it? I used to think that iron that's in cereal was iron. It is. Is it? Yes. Metal?
It's,
yes.
it is.
I know.
You can change.
That's why.
If you want to do something, do you eat cereal?
Not really, but what?
Okay, take his cereal down and see if it's iron fortified, quote
Okay,
unquote.
yeah.
It's iron fortified, then it has little bits of iron in it.
Yeah.
And you can take a magnet to the cereal.
Pull them out.
Uh-huh. Yeah.
That's crazy. I
Yeah.
said this to my friend. She didn't believe me. I was like, see, this is why we have this conversation.
Yeah.
So,
Especially if you have a rare earth magnet, it's a really strong magnet. And all you do is you put the cereal in a baggie and you take the magnet so it doesn't get all files all over it. And yeah, and it'll end up and you shake the
that's crazy. And that's
and it ends up being rust, really. What you're eating is rust.